Hello everyone, thanks for watching my talk on the fractional calculus based homogenization technique application to the dynamic analysis of periodic beams. So first a brief overview of my talk. I will begin with the motivation behind this study and then I'll introduce fractional calculus and the fractional calculus based homogenization theory with a particular specific application to heterogeneous beams, and then I'll discuss a strategy to derive the different fractional model parameters describing a heterogeneous beam, and then I'll present some results and the broad conclusions from this study. So the rapid growth in the field of periodic and architecture materials has further highlighted the need for accurate and efficient computational methods capable of predicting the dynamic behavior. Now, periodic and architecture materials have important applications, for example, in wave collimation, in wave guiding and wave shaping, to develop broadband attenuation techniques, and for example, for far field imaging and far field magnification and focusing. Now, because of this lot of applications, as I said before, we need to predict the behavior and response of these structures very accurately. A lot of techniques have been developed in literature for their modeling. Examples include spatiotemporal discretization techniques, which include model order reduction, finite difference and finite element methods, plane wave expansion methods, and low frequency homogenization techniques. In low frequency homogenization techniques, we call that we use homogenized material properties or homogenized geometric properties to describe the response of a complex system. Low frequency homogenization techniques have been very recently expanded in the literature to develop high frequency homogenization techniques where asymptotic multiscale expansions about the homogenized material properties are used to capture the variation in the heterogeneous materials and their effect on the response of the overall periodic or complex structure. Now, these methods are very powerful and they have been able to address a lot of computational issues which were initially faced for these type of materials, but some limitations still persist. So, for example, in spatiotemporal discretization methods, we know that there is an implicit trade-off between accuracy and computational time. Now, so these methods are likely to fail in porous and fractal media where there are a lot of spatial scales, fine spatial scales and fine temporal scales in dynamic response. And to capture these fine scales, we need a very high computational cost, very small fine discretizations. Now, low frequency homogenization techniques typically fail to capture the existence of frequency band gaps, the location of frequency band gaps, and consequently the response of these structures in these band gap regimes. While high frequency homogenization techniques accurately capture the existence and location of band gaps, a few limitations of high frequency techniques stem from their intense theoretical derivations resulting from the multi-scale expansions and the ensuing computational costs. So in order to address these issues, we use fractional calculus to develop a fractional calculus based homogenization theory. So fractional order operators are basically different integral operators which allow us to differentiate functions to any real or complex order, not necessarily integer order like we do in classical calculus. Several definitions for fractional derivatives exist. For example, the Caputo, the Riemann-Liouville, and the Grunwald-Letnikov. I will leave those for further exploration, but in this study we use the Caputo definition of fractional order derivative. The reason being that Caputo derivatives lead to integer order essential boundary conditions which have a clear physical interpretation, unlike other definitions which sometimes lead to fractional order boundary conditions, essential boundary conditions, for which we do not have a physical interpretation. So this is the so let us look more at the definition of the fractional order derivative and understand what it does. So basically it takes a local information and over a memory integral it convolutes with a power law kernel, typically the attenuation kernel, and it so captures the information which lies behind of the point. Basically this is the left-handed derivative. It captures the information of a lot of points lying behind of a point. Similarly, we also have the right-handed derivative which captures information lying ahead of the point. and a combination of these two can be used to capture information from an entire horizon, and this is typically known as the Rees-Caputo derivative. So basically, fractional order operators allow us to perform homogenization over a particular horizon of influence, capture the information from particular horizon of influence. So now we use fractional calculus to develop a homogenization theory for heterogeneous beams. For this purpose, we use Euler-Bernoulli beam kinematics, but I should remark that we can directly extend the formulation presented here to Timoshenko beams as well. So following the fractional order homogenization theory, we define the strain in this heterogeneous beam by using fractional order derivatives of the displacement field. So here d alpha x is the fractional order derivative. When we set alpha is equal to 1, we recover the classical definition, which we use in classical continuum mechanics. Now recall that this fractional order derivative is a Rees-Caputo derivative that I highlighted in the previous slide, wherein the left-handed derivative captures information which lies behind of a point, and the right-handed derivative captures information which lies ahead of the point. So in this way, the non-local derivatives will be used to capture the information of heterogeneity and its impact on the response of the beam. Then we define the stress in the homogenized beam using the fractional order homogenization stress in the following linear manner. So using the constitutive relations for the stress and strain in the previous slide, we can define the potential energy, the kinetic energy, and the work done on the beam. And then by using the Hamiltonian's principle, we can derive the governing equations, the boundary conditions, and the initial conditions. I don't want to go detail into the math. It can be found in one of my papers where we where we use fractional calculus to model non-local beam. But I must say that the process is similar. The key thing I want to highlight here is that these governing equations are positive definite and self-adjoint, and they accept a unique solution. This is critical to ensure a proper numerical implementation, for example, by finite element methods, which we do in this study. We introduce two parameters here, the fractional order alpha and the other dimensional constant L tilde. Since L tilde was used for dimensional consistency, we can set it as 1. But the question still remains, how do we find alpha? So here we find alpha by matching of beam dispersion and the fractional order dispersion relations. The fractional order dispersion relations can be derived by assuming harmonic wave ansatz in the governing fractional order governing equations in the previous slide, and the beam dispersion relations can be derived by analytical methods for periodic beams or resorting to finite element techniques for complex heterogeneous beams. Now after some mathematical simplifications, we obtain a more simplified expression for alpha. There are two important remarks here. First, fractional order models typically help capture anomalous attenuation in different complex systems, which we have shown in this paper in proceedings A. And the other thing is, we expect this alpha to be complex in general. So what does a complex order fractional derivative now signify? So in this famous paper, Professor E. R. Love has shown that complex order fractional derivatives help capture frequency dependent modulation of phase and amplitude. So we leverage these two characteristic features here to model the spatial attenuation in frequency band gaps of periodic structures in this study. Now in this study we consider an aluminium brass periodic beam, and this is the dispersion relation which we derived analytically, and using the expression in the previous slide we derived the fractional order alpha describing this periodic beam. Now note that in these band gaps the alpha is complex in number. The alpha is a complex number. So we expect that this alpha will help us model spatial attenuation in these band gaps, and for band pass frequencies the alpha is 1. Now we modeled this periodic beam at 4 different frequencies to show different characteristics. We simulated it using the fractional order finite element method and then compared against COMSOL predictions. So first, the frequency was located within the driving frequency was located in the first pass band, and this was the response we observed. So the predictions of the fractional order method and the COMSOL match very well. Next, we simulated this within the first band gap. Now recall that low frequency homogenization techniques typically don't capture the spatial attenuation within band gaps, but the fractional order method, as you can see here, captures this very well. So this Within this band gaps, the imaginary value for alpha helps us model the spatial decay in the response. Now the same is also observed for the second band gap. We capture this spatial decay very well. Now one limitation of the fractional order method is noted when we move to the second pass band. So here we see that the fractional order model is not able to capture the forward propagating and back scattered waves which interfere in this short wavelength regime. So we are looking to address this limitation by using more advanced operators, for example, the variable order operators, but that is a future study. So I want to conclude this talk by stating that the fractional order technique was a very powerful technique which helped us to model spatial attenuation in frequency band gaps and extended the range of applicability of classical homogenization techniques. Although we applied this technique for 1D periodic systems, we can extend it for higher dimensional periodic systems, and we anticipate that the fractional order technique can be the foundation for the development of more complex techniques where we can combine the strengths of both high frequency and low frequency homogenization methods. So I want to conclude by thanking my advisor, Professor Sampalotti, and to our funders, NSF and